Hello everyone, Mr. Hasty here. Today we're going to be talking about section 8.2, which is on the properties of waves. So before we go into that, let's have a brief discussion about some of the terminology we're going to need today. When we talk about waves, I will usually draw a transverse wave just because they're easier to draw for me than longitudinal waves. So some of the terminology associated with waves that we need to remember is that the top point is called the crest, and the bottom point is called the trough. That won't come up too much today, but it's a good reference point. The wavelength, which we will talk about a lot today, is the distance from any point on a wave to a similar point on the wave. Now, wavelength is one of the things we're going to be talking about a lot today. And so when we work with wavelength in an equation, because we're going to be doing some math today, we usually measure it in meters. And the symbol we use to represent it is a Greek letter called lambda. And that's a little weird. We don't normally use the Greek letters. This might be one of the first times you've ever used a Greek letter in algebra, but that is the Greek letter lambda. Looks kind of like an upside down Y. And the only reason we're going to use that is because that's what every textbook that you're going to see from here through the rest of your science career is going to use for wavelength. We're going to talk about the period. Now, what a period is, if you remember, is how long it takes for one wavelength to occur. And we measure periods typically in seconds. And we use a variable, capital T. That stands for big time, like how long is one full cycle, one time. A related concept that we're going to talk about is frequency. Frequency is a measure of how many waves per 1 second. So if something has a frequency of 25, that means it would have 25 waves per second. The measurement for this is going to be something called a hertz. Hertz is, which we abbreviate Hz. Now, the tricky part about frequency is we say waves per second, but what a hertz actually is, a hertz is equal to 1 over a second. It's a little bit odd, but it doesn't come up too much. The big thing to remember is that frequency is measured in hertz. And if we need to, hertz is 1 over seconds. So the formula we're going to have for frequency is just 1 divided by your period. So if we ever need to do a calculation with a frequency, but all we have is a period, we just take 1 divided by that period and it gives us the frequency. The last concept we're going to talk about is the velocity that a wave travels at. The formula for that is the frequency times the wavelength, f times lambda. You can get the velocity of any wave by taking its frequency times its wavelength, f times lambda. Now the velocity will typically be measured in meters per second, just like all velocities we've worked with this year. Now that we have those bases and these basic formulas, which you're going to want to know, especially this guy right here, we're going to use him a lot today. We're going to do some examples. Example 1. A water wave has a wavelength of 0.5 meters. So that means lambda equals 0.5 meters. And is moving at 4 meters per second. Well, meters per second is a velocity, so we know the velocity of the wave is 4 meters per second. What is the wave's frequency? So we're looking for frequency. The formula we were given was that velocity equals frequency times lambda. fill in the information we have. 4 meters per second for velocity. Frequency we don't know. And lambda is 0.5 meters. We divide both sides by 0.5, just like every algebra equation we've done like this. And we're going to get that our frequency is equal to 8. 8 what? Every problem that we do in this class needs units. So frequency is measured in hertz. What that means is that there are 8 waves per second. So this water wave is making 8 waves every second. All right, example 2. An FM radio signal has a frequency of 96 million hertz and a wavelength of about 3.1 meters. Now these numbers are actually fairly accurate. 96 million hertz seems like a lot, and it is, but a lot of waves like radio waves, light waves, move at incredibly high velocities, the speed of light for instance, and thus they have incredibly high frequencies. So we want to know the wave's velocity. So we know that the frequency is 96 million hertz. And we know that the wavelength, which we call lambda, is 3.1 meters. What we're looking for is the velocity. So we take our formula, V equals F times lambda, and we fill in the information. 96 million times 3.1. And when we do that, we get 297,600,000. And that is a velocity, so it'd be measured in meters per second. Turns out this is the speed of all electromagnetic waves. Light, radio waves, gamma rays, all those move at that velocity, which is incredibly, incredibly fast because it is the speed of light after all. Let's go into a couple more examples. A slow spring has a frequency of 0.5 hertz, so it's 0.5 waves per second. So that means one wave every 2 seconds. So our frequency, wrong thing there. Our frequency is 0.5 hertz, and it has a velocity. Speed and velocity can be synonymous in this case. 2.5 meters per second. We need to determine the spring's wavelength. We want to find lambda. So, using our formula. Oop, made a mistake there. All right. Velocity equals frequency times lambda. Fill in the known information. I know the velocity is 2.5 meters per second. And the frequency is 0.5 hertz. Just like every other algebra equation that looks like this, we divide by 0.5. Now I'm going to get 5 for my wavelength. And wavelength is measured in meters. So that means this spring's wavelength is 5 meters. All right. This last one's a little bit tricky. A wave has a period. So that's a red flag. That's not one of the things we've been using. A period of 2 seconds and a wavelength of 0.25 meters. So I know my period, which is t, is 2 seconds. And I know my wavelength, lambda, is 0.25 meters. But I want to know the velocity. So our velocity formula asks us to have frequency and wavelength. We don't have frequency. We have wavelength though. So we got to find a way to use the other information we're given, that t is 2 seconds, to find our frequency. So we turn to another equation. That equation is that frequency is 1 over the period. So in this case, frequency is 1 over 2 seconds. We could leave that as a fraction, or we're going to call it 0.5 hertz. Now I know my frequency, I know my wavelength, and so I can find my velocity. My frequency is 0.5 and my wavelength is 0.25. So we just do that multiplication. We come up with 0.125. Let's talk units briefly. So this is a velocity, so that'd be meters per second. That's a pretty slow wave. All right, there are going to be practice problems associated with this. So make sure to review these examples, try the practice problems, and we'll talk about the solutions later this week. See you next time.